Welcome to The Explainer. Today, we're going to become diagnostic detectives. Our mission is to understand the secret language of machines, decoding their vibrations so we can stop failures before they even happen. You know, every rotating machine, whether it's your car's engine or a massive power plant turbine, vibrates. That's totally normal. But sometimes, a tiny change in that vibration is actually a cry for help. It's an urgent warning that something is about to go catastrophically wrong. The real trick is knowing how to listen.
And believe me, listening has never been more critical than it is today. As engineering just keeps pushing the limits, our machines are getting faster and lighter. They're being asked to run longer and harder. So that means catching a tiny fault early on can literally be the difference between a simple, quick repair and an absolute disaster.
So here's a look at our usual suspects. We're talking about everything from a simple unbalance to really complex gear defects. Each one of these problems leaves its own unique vibrational signature, and our job is to figure out which is which. Okay, let's really dive into this. To solve these mechanical mysteries, we need the right tools. You can't just put a stethoscope up to a generator, right? No, we need something way more precise to translate those vibrations into data we can actually use. So our primary method of investigation is something called vibration analysis. Honestly, you should think of it like industrial forensics. We're capturing the raw vibration signals from a machine, and then we break them down to find the clues that are hidden deep inside. And this, right here, this is our main clue sheet. It's called the fast Fourier transform, or just FFT spectrum for short. This chart is basically the machine's unique vibration fingerprint. Along the bottom, you have frequency, and on the side, you've got amplitude, which is just the strength of the vibration. Every single peak you see on this chart, it tells a story.
The most fundamental clues we're looking for are these peaks, and they happen at multiples of the machine's running speed. We call them 1x, 2x, 3x, and so on. X is just the running speed. The location and, just as important, the height of these peaks, those are the tells that help us pinpoint exactly what's going wrong.
All right, so now that we've got our decoder ring, let's take a look at the most common culprits and the telltale fingerprints they leave behind, and we'll start with the one we see most often. Our number one suspect is unbalance. All this means is that a rotor has an uneven distribution of mass, kind of like having a heavy spot on your car tire. It is by far the most common defect you find in rotating machinery, but thankfully, it's also one of the easiest to spot. And this just illustrates the connection perfectly. On the left, you see that uneven mass. Well, as it spins, it creates this powerful force once per revolution. The result? Look at the right. It's a clean, super dominant peak right at that 1x frequency. See that huge spike? That is the machine basically screaming, "I'm unbalanced." Next up, we have misalignment. This happens when two connected shafts aren't perfectly lined up. It really comes in two main flavors. You've got angular misalignment, where the shafts meet at an angle. And then there's parallel misalignment, where they're offset but still parallel. Each one creates a totally different kind of stress on the machine.
So for angular misalignment, the force kind of pushes back and forth along the shaft itself. That's what we call axial vibration. And this creates a more complex fingerprint. You get significant peaks showing up at both 1 and 2 times the running speed.
Now, with parallel misalignment, that offset causes the shafts to basically bump each other twice during every single rotation. And as you can see, this makes that 2x peak in the up and down or radial direction the really dominant clue in the vibration signature.
And then there's this. If the fingerprint looks like a total chaotic mass of peaks, I'm not just talking 1x and 2x, but tons of multiples and even weird submultiples like half x. The culprit is almost certainly mechanical looseness. This is the sound of loose parts just rattling all over the place, creating a complex, noisy, and really unstable signal.
So let's look at how these fingerprints can actually change over time. You see, some faults don't just happen all at once. They're more insidious. They grow slowly, and their vibration signatures evolve as they get worse and worse. And rolling element bearings are the perfect example of this. They don't just suddenly fail. They tell a story of their own decline. And by listening closely, we can actually track their entire life cycle and predict exactly when they need to be replaced. It all unfolds in 4 distinct stages. In stage 1, all we can hear are these ultrasonic whispers, stuff you can't even hear with your ear. By stage 2, tiny pits start to cause the bearing components to ring like a tiny bell at their natural frequencies. Then in stage 3, the wear becomes visible, and it creates these clear, distinct peaks in the spectrum. And finally, you get stage 4, where the bearing is so damaged, it creates a chaotic roar of random noise, right before it completely fails.
So we've cracked a few cases, we've seen how to identify unbalance, misalignment, and failing bearings, but what's the real-world impact of all this, of being a diagnostic detective for machines? Why does any of this actually matter?
Well, that brings us to the most crucial point. This isn't just about fixing things that are already broken. No. This is about a fundamental shift from reactive to predictive maintenance. It's about using data to see into the future and to act before a problem even really develops.
Understanding this secret language is literally what keeps our world running. It's the difference between a planned, inexpensive bearing replacement and a catastrophic failure that shuts down a whole production line for days, costing millions. It helps prevent blackouts, it enhances safety in jet engines, and it keeps our entire global supply chain moving by making our factories smarter and a whole lot more reliable.
Ultimately, what we're looking at here is such a powerful concept, translating incredibly complex data into clear, actionable insight. And that's a skill that goes so far beyond just engineering. It makes you wonder, what other vibrations, what other hidden signals in the systems all around us could we learn to decode if we only knew how to listen?